So, welcome student to the next class of Introduction to Nonlinear Optics and its application. So, today we will have lecture number 45 and today we will start a topic related to third harmonic generation and corresponding energy conservation. So far we have been discussing about the cell phase modulation and find that when the nonlinear effects are there are two kinds of effects that happens. One is the self focusing and another is the cell phase modulation. Self focusing is a special phenomena where the self focusing cell phase modulation is a temporal phenomena, or this is a phenomena where the light can be considered in the distribution of the light, the phase of the light will going to change. So, today we will going to find out another fundamental effect of chi3, which is the third harmonic generation. So, it is technically exactly the same, the treatment wise it is exactly the same that we have done in our previous class for second harmonic generation, where we launch a light of frequency omega and we are getting a frequency 2 omega. This is a different kind of frequency mixing. Here we will going to have exactly the same thing. I am launching a frequency omega and going to have a frequency 3 omega, provided some phase matching conditions are there. So, we will derive the equation of third harmonic and then find that because of the third harmonic generation whether any kind of energy dissipation will be there or the energy conservation will be still valid for third harmonic generation or not. So, today we will have two topics, third harmonic generation and the corresponding energy conservation. Well, for third harmonic generation, so third harmonic and energy conservation. So, for third harmonic generation, again go back to this schematic diagram. This is a schematic diagram suggests how the third harmonic will going to generate as well as how the Carr effect will originate. So, this is a medium where we have chi3 equal to 0. If chi3 equal to 0, what happened? The electric field is launched with the frequency omega. Nonlinear polarization is epsilon 0 chi3 E cube. Due to this E cube term, we have third harmonic. So, nonlinear polarization term will have frequency component 3 omega, and this 3 omega frequency component will allow the dipole or with be a source term for the dipole that will going to vibrate with a frequency 3 omega. Once the dipole will vibrate with a frequency 3 omega, it will start generating an electric field of 3 omega, and that is basically the origination of the third harmonic generation. So, this is a total picture or the physical picture of the third harmonic, where the electric field of omega is launched and we will have electric field of 3 omega. So, how these things will happen we will study in detail by using this our mother equation, which is nonlinear Maxwell's equation. So, exploiting nonlinear Maxwell's equation, we try to derive the evolution of the amplitude of the third harmonic wave as well as the fundamental wave. So, here the total electric field will be the combination of the electric field. So, there are two electric field inside the medium already. One is E omega, if I write E1 omega, another is E3 omega. These are the two fields E3 3 omega. These are the two fields that will be inside the system. One is E1 omega and another is E3 of 3 omega. 3 omega means it will vibrate at 3 omega frequency, omega means it will vibrate at omega frequency. Well, if I now write the total field, it will be the combination of their complex conjugate, so that this total field become a real field. So, E1 omega E1 of omega star, E3 of 3 omega E3 of 3 omega star. 4 fields are there. So, P nonlinear will be total field whole cube, electric field component E omega, electric field will component E omega can be represented at half E1 e to the power I k1 z omega t and half E3 e to the power I k3 omega minus 3 omega t for electric field with 3 omega frequency. P nonlinear will be total field cube. So, total field is this. So, cube of that means again we will have several frequency component in P nonlinear. This is not the first time we are using this equation. So, we will see that there are many frequency components are there, and we can identify these frequency components, identify the terms. For example, this is the cell phase modulation term that we have been calculating for in the last class. We are calculating this term. This is the cross phase modulation, this is the cell phase modulation term SPM, this is a cross phase modulation term, and finally we will have a term which is related to the third harmonic generation. This is not a third harmonic generation term because its frequency component is omega, but this term will be for a term related to third harmonic with omega field. In the similar way, for P nonlinear 3 omega, we have 3 terms. This is the cell phase modulation, this is cell phase modulation related to omega field, cross phase modulation related to omega field, third harmonic generation term due to the omega field. This is not a third harmonic generation term critically, but this is a term which corresponds to third harmonic generation. Here we have a third harmonic generation term because here the frequency is 3 omega. So, third harmonic generation term. This term is for cross phase modulation term with frequency 3 omega, for frequency 3 omega, and this is cell phase modulation term for frequency 3 omega. So, 2 fields are there. Individually for 2 fields we have cell phase modulation, cross phase modulation and 3 omega term and third harmonic generation term, and for other 3 omega frequency we have also third harmonic generation, cross phase modulation and cell phase modulation for that particular field. So, once we identify the field, then as I mentioned, we need to only consider, since we are dealing with third harmonic generation, we need to only consider the third harmonic terms, third harmonic generation terms inside this P nonlinear. So, in P nonlinear omega, this field is related to third harmonic. So, I write this field here, this part of the this part, and for P nonlinear 3 omega, we only write the third harmonic term, which is this one, and I write this here. So, 2 term we identified, one is for third harmonic generation with corresponding to omega, and another is third harmonic generation corresponding to 3 omega. So, we identify these 2 terms for P nonlinear and extract these 2 terms from these total terms. This degeneracy factor, again you need to consider very carefully that how these 2 fields are interacting. Based on that, this degeneracy term will be there. If 2 distinct fields are there, then we will have 3. If 3 distinct fields are there, we have 6. If 1 distinct fields are there, then we have 1. For example, this is related to 1 distinct field and this is E1. Every field and their complex conjugate are considered as a distinct field. Well, next we need to solve the Maxwell's equation, and in order to solve the Maxwell's equation, here the source term is third harmonic. So, that means E1, how this E1 is going to evolve, we need to find out, and in order to find out the evolution of the E1, we need to write the source term for P nonlinear, from P nonlinear, which containing omega term, and that is related to the third harmonic. So, E1 is given like this, where E1 is the amplitude of the fundamental field, and P for P nonlinear, the 3 omega, the third harmonic generation term we extracted, it is E3 E1 star square e to the power of I. A phase term is associated is there, k3 minus 2 k1 z minus omega t, it has to be a frequency component omega. And next what we will do, we just write this, try to find out what is the value of this del square E1 omega. So, del square E1 omega is simply this term, because we are using this thing almost I mean for every class we solve this Maxwell's equation for a given E1. So, if E1 is given, so the double derivative corresponding to this thing is this, where this delta square is one dimension, it is equivalent to del 2 del z square, because x y components are not there. So, once it is there, so we can solve, we can make a derivative of this quantity, this term, and once we make a derivative, we will have double derivative of E1, single derivative of E1 with respect to z with a 2ik multiplication, and then k1 square E1. Again we use the slowly varying approximation, so that this term will not going to affect, it is varying slowly. So, this is much smaller than this. So, once this is much smaller than this term will be approximated, and if I approximate, this will be this quantity, and the double derivative with respect to t of E1 is simply minus omega square E1 e to the power I k1 z omega. So, left hand side we almost calculate, we calculate this term and also we calculate this term, and we know that eventually this term will cancel out with this one, because these two things are same with this multiplication. When I multiply this quantity here, these two terms will be same and eventually cancel out. The next thing is to find out what should be the source term here, how the source term will come. Well, third harmonic term as a source, as I mentioned, if I use this, then we will find this is my third harmonic source term. If I make a double derivative with respect to t, so only t is sitting here, so we will have a minus omega square term, only this. So, once we have a minus omega square term, then we have all our terms, the left hand side and right hand side. If I put left hand side and right hand side together, then we find that this term and this term will cancel out, and we will this leads to an expression like this. So, in the right hand side we have E3 E1 star square e to the power I k3 2 k1 z, and here we have e to the power I k1 z. Here I should make one note that when we calculate the cell phase modulation in the previous class, we find that in the left hand side and right hand side it is automatically phase matched. So, the phase match term e to the power I kz minus omega t was appearing for both the cases, both the sides. So, it was simply cancel out, but here we find that here we have e to the power I k3 minus 2 k1 z, and in the left hand side e to the power I k1 z. So, there is no way they can cancel out each other. So, we need to take care of this term also. So, one phase term will be there exactly like the second harmonic generation, one phase term will be sitting here. So, we are almost in the so from this now we have equation like this. So, this equation can again simplify, and once we simplify this equation, I write 2 ki. So, this 2 will be 8 here because there is a 4 sitting in the denominator. So, 4 into 2 will be 8. This I, this minus 1 is there, so 1 it should be I. This k will be sitting here, and if I use the value of k is again omega divided by c in 1. So, if I write this k as omega divided by c in 1, so omega divided by c term will cancel out and 1 omega divided by c will be there and 1 n 1 will be there, and e to the power k3 divided by 3 omega. So, here it should be, so here it should be 3 omega, it is written wrongly, because once we 3 omega it should be simply 3 omega and it should be simply 3 omega. 3 omega, 3 k1 and 3 k1, not 3 omega, this is 3 k1, 3 k1. Well, it is written by mistake, it is written 2 k1. So, delta k will be k3 minus 3 k1. This is the phase mismatch, and if I write this phase mismatch in terms of delta k, my total equation becomes something like delta E1 z, it is the evolution of the E1 is I 3 by 8 chi 3 omega divided by c n 1 E3 E1 star square e to the power I k z delta k z, where delta k is k3 minus 2 k1. Well, once we have the evolution of delta E1 delta z, in the similar way, exactly in the similar way, you can find out the evolution of delta E3 delta z, that means this equation, and you will need to follow exactly the same procedure that we have done for dE1 dz. This is rather more important, that is why I again put this as a homework, and for this homework you need to use this equation, which is the nonlinear Maxwell's equation, your starting point. Then you need to use E3 at 3 omega, this form, and put this here. When you put this here, you need to make a derivative of this quantity where E3 is a function of z and k3 is there. So, again you will have a 3 term with E3 and k3, and then you need to make a derivative of this E3 with respect to time, you need to make a second order derivative. After doing that, the source term is sitting here. So, this source term for third harmonic generation you can pick up from your p nonlinear third harmonic with 3 omega. It should be simply E1 e to the power I 3 k1 z omega t, that means it will have a frequency 3 omega because 3 is sitting here. And if you calculate these things carefully, then you will ended up with this expression, which is equation 2 and which is the evolution equation for E3. So, now we have a evolution equation of E1 and also we have a evolution equation of E3. So, now two equations are in our hand. These two equations are again coupled equation, and these two coupled equations are now need to be solved. So, before solving, let me give you a summary. So, how you calculate these two things? So, you start with nonlinear Maxwell's equation, and then both the cases you find out what is your E1 omega and what is your E3 3 omega, that is the fundamental wave and this is the third harmonic wave. You put these things here and find out what is your left hand side. In the right hand side you have a source term, and this source term, depending on the problem, you need to choose the source term. If you calculate the cell phase modulation, you need to find out the p nonlinear for cell phase modulation, which we have done in the previous class. If you try to calculate the third harmonic generation, you need to pick up the p nonlinear term for third harmonic generation, and p nonlinear for third harmonic generation is this. You calculate this derivative for this given term and put these things again to the Maxwell's equation, solve this Maxwell's equation, and this equation will leads to an expression of E1. In the similar way you can do here also. You calculate, you write your E3 in this form, then you calculate the P nonlinear term for 3 omega. This is for third harmonic generation. So, you just pick only the third harmonic generation term in P nonlinear. You have this term in your hand. Once you have this term, you combine this and put it here in the Maxwell's equation, and you will have another expression which is similar to this. This is the coupled equation, and these two coupled equations gives you the third harmonic. So, E3 is the amplitude of the third harmonic term. So, we need to mind it, we need to find out E3 by solving these two equations together. Well, once we have these two equations, finally we need to check that whether the energy conservation is valid or not. Let us understand once again what is going on. I launch E1 as a frequency omega here in the system. Inside the system, E1 is there, which is a fundamental wave, and also E3 is there, which is third harmonic term. Now, E1 and E3 will going to evolve because they are the function of Z. So, we should have a differential equation of the amplitude of E1 and E3, which we have, and these are the equation of E1 and E3, differential equation of E1 E3, which are coupled to each other. Under phase matching condition, you can omit this term, but without phase matching this term will be there as usual. And now, if I write the intensity of these two things, then intensity of the fundamental wave E1 can be represented in this way, which is the equation of that, and intensity of the third harmonic generation will again written in this form, half epsilon 0 C n3 mod of E3 square. Several times we are using this expression. So, by that time you are familiar with this representation. Now, the next thing to find out whether the total intensity or the total energy is conserved under this or not, because for this coupled equation you can readily understand that third harmonic will going to generate because of the pump here of the fundamental wave. So, the fundamental wave basically gives the energy to the third harmonic to evolve. So, that means there is some energy exchange between third harmonic and the fundamental wave, exactly the way second harmonic was generated. Here we are doing the same thing. So, energy is coming from fundamental wave to the third harmonic. When the energy is coming from the fundamental wave to the third harmonic, then we need to find out that these two equations are consistent with the energy conservation or not, whatever the two equations we derived. So, in order to find that, what we do, that we find d I dz, this is the total intensity. So, total intensity is the derivative d dz of I1 plus I2, because I1 and I2 is the total intensity which is equal to I. So, I1 dz again can be represented in terms of E1, because I1 is this. So, if I make a derivative of this, half of epsilon 0 C n1 will be here, this is a constant term, and the derivative of these things will be simply this. Now, d E1 star dz, we know that this quantity, because this is the expression that we have in our hand. So, if I put, then what happened, that I need to take this common with I. So, if I take this common, we will have 3 divided by 16 epsilon 0 chi 3 omega in the outside, and in the inside we will have E3 cube E3 star e to the power of I delta k z plus E3 I cube E3 to the power I delta k z, these two terms. In the similar way, if I do for I3, we will have the same term, only a negative sign will be here. So, this term will be sitting here with a negative sum and this term will be sitting here with a positive term. Please do that and check it by yourself. So, once we have this equation together, then we can find one expression that d I1 dz is equal to minus of d I2 dz. So, if I add these two things, we will have dz1 I1 plus I3, which is equal to di dz is equal to 0. That means, the total intensity will remain conserved or the total energy will remain conserved. So, in the third harmonic generation process, whatever the expression we derived is consistent with the energy conservation. So, this equation is also known as the Manley-Rowe relation, which is also a similar form for second harmonic generation. Only thing is here, okay, here one mistake we have done again, and this should be I3 not I2, because I am making a notation here for I3. So, it should be I3 I1 I3 anyway. So, exactly like the third harmonic second harmonic generation, for third harmonic generation we find that the coupled equations for fundamental wave and third harmonic wave are consistent with the energy conservation. That means, the total energy will remain conserved. So, it is called the Manley-Rowe relation. From this Manley-Rowe relation, we can also find that the number of photon that is transforming from the fundamental to the third harmonic is also conserved. So, this conservation on energy actually confirm that whatever the equation we derived is correct. So, with this note, let me conclude today's class. So, thank you for your attention and see you in the next class, where we discuss more about the cross phase modulation and other phenomena related to the third order effect. So, thank you for your attention and see you in the next class.